we see a curved lens or a curved mirror for that matter, we know there's two types, converging and diverging. Remember, converging lens is a convex lens. A converging mirror is a concave lens. We don't want to use those terms convex and concave. We want to use the terms converging and diverging. So if you happen to see convex, concave, translate it to converging, diverging. Now, the nice thing about these things is that whenever we have a converging lens or mirror, it doesn't really matter, the characteristics ends up being exactly the same. Whenever we have a diverging lens or a mirror, it doesn't matter whether it's a lens or a mirror, the characteristics of the attributes end up being exactly the same. So let's go through a quick little review of the characteristics that we'll see for converging lenses / converging mirrors. Again, exactly the same. You can draw the ray diagrams every single time you get a question, or you can remember some patterns like we reviewed yesterday, and we're going to review again here right now. This is converging something. Converging lens, converging mirror, it doesn't matter. The images end up being exactly the same. This is going to represent f, a distance of f. This is going to represent a distance of 2f. When I make my object distance way out here, this is my object, not my image. When I make my object distance way out here, I always get an image that has what characteristics? Larger, smaller, same size? Larger. No, actually it's not larger. You almost tricked me there for a second. What is it? Smaller. Yeah, the image is going to be smaller. The image is going to be right side up or upside down. Don't look at what we see right there because that's our object, right? Our object is right side up. Our image is going to be inverted, yeah. And is it going to be real or virtual? What is it? It's going to be real. We've got a smaller, we've got an inverted, we've got a real image. Always, whether it's just a little bit beyond 2f or it's a lot beyond 2f, the image will be smaller, it's going to be inverted, and it's going to be real. Now, let's put our object right at 2f. Again, our object is the same size as it was before, but the image characteristics will be a little bit different. Is this image going to be larger, smaller, or is it going to be the same size as the object is? It's going to be the same size, right? Is it going to be upside down, inverted, or is it going to be right side up? It's going to be inverted. And is it going to be real or virtual? It's going to be real. So you can start seeing a little bit of a pattern forming here. Both inverted, both real, but one is larger, one is going to be same size. You can probably predict what was going to happen next, even if you didn't remember what was going to happen next. Based on these two, what do you think the next one's going to be? We had smaller, we had same size, now we have larger, right? If we have an object that's placed in here, the image is going to be larger. It's going to be inverted or real. Sorry, inverted or upright. Stephen, is it going to be inverted or is it going to be upright? Sorry? No. We keep following the same pattern. Smaller inverted real, same size inverted real, larger inverted real. That make sense? What about the next one here? If we have an object that's placed at the focal point, this is kind of a kaboom one, right? This is where everything blows up. We see the pattern, smaller inverted real, same size inverted real, larger inverted real, and then something completely different happens. We end up having, in this point, no image formed, right? No image formed. And then we put our object in here, inside the focal length. DO is less than F. Completely different, right? Now we have an image that is larger, smaller, same size. That's the only thing that's the same about it. We've got larger image formed here. Is it going to be inverted or is it going to be right side up? It's going to be right side up. Remember, the size of it's the only thing that's the same. It's upright. Is it going to be real or virtual? In this case, it's going to be virtual. Good. So if you have a converging lens, you have a converging mirror, it doesn't matter which one it is. These are the characteristics that are formed. Now, if we have a diverging lens, a diverging mirror, I'm not even going to draw the position of the object in various places, because if you have a diverging lens or mirror, the image characteristics are always going to be the same. We don't need to worry about where the object is placed. A diverging mirror or lens always produces an image that is larger, smaller, same size. Smaller, yeah, it's smaller, and it's going to be right side up or upside down. Mason? Upright. And is it going to be real or virtual? Virtual, yeah. So you can see a few patterns forming here, right? Just smaller inverted reel, same size inverted reel, larger inverted reel, kaboom. And then we have larger upright virtual. You also see the diverging is always the same, but you also see a few smaller things as well. For instance, if you have a real image, we have three situations where we have a real image. If you have a real image, the image is always going to be inverted. If you have in a virtual image, the virtual image is always going to be upright. Okay, does that make sense? A few different things there. Now, let's take a look at the questions that we wanted to look at here, and that was practice question set number 23. I want to look at question number 2 first. It relates more closely to what we just did than question number 1 does. Question number 1 is a pretty challenging question as well. Question number 2, we can do it a few ways, including what we just did. First way, we could draw a ray diagram, right? We look at this question here. Object is placed 35 centimeters from a diverging lens. Here's a diverging lens. The focal length is 20 centimeters. So this is 20. Okay, this is 2F, 40. This is where our object is. We could draw the ray diagram here. We could determine what the characteristics of this image are based on this ray diagram. Okay, got it, done. The second way we could do it is, we could remember our patterns here. If we have an object that's placed midway between F and 2F, the image characteristics would be larger inverted reel. So either of those ways give us an answer that is, sorry, made a mistake here. Made a mistake. This is a, what was my mistake here? What did I mess up on? Yep. This is diverging. We should, like I've told you guys this before, and yet I didn't follow my own advice. We should draw attention to the fact that it's diverging so that we don't miss that, right? If it's a diverging lens, a diverging mirror, remembering the patterns tells me that it's always going to be smaller, upright, and virtual. Remember the patterns, draw the ray diagram, doesn't matter. The answer is going to be D, virtual and smaller than the object. Now there is a way to do this mathematically as well. We could say that DO is 35.0 centimeters. We could say that the focal length is negative 20 centimeters. How come it's negative? Because it's diverging, right? Let's find the value of DI here. DI is found by the lens equation. 1 over F is equal to 1 over DO plus 1 over DI. F is 1 over negative 20. DO is 35. And DI is, this is what we're looking for here, in this question at least. Let's say negative 20, 1 over negative 20, subtract 1 over 35. Let's flip that over. We get negative 12.727. The fact that that's a negative value tells us what? Remember, F, DO, and DI, positive, all mean real. M, HI, and HO, positive, mean upright. This is a negative DI. That means that the image is, what is it? Virtual, right? The image is virtual. So that means the answer is either going to be C or D, right? Now, how do we know that the image, mathematically, the image is smaller? Well, we could take a look at the magnification equation. Now, M is equal to negative DI over DO. We could say negative 12.727 divided by the object distance, which is 35. I don't know exactly what that works out to be, but I do know that it's going to be 0 point something, right? Which means the image is smaller. If it's a number that's less than 1, the image is smaller. So the answer has to be D. So draw your ray diagram. That's fine. Remember the patterns. That's fine. Do the math. That's fine. It works in all 3 ways. You guys did this last week, but does anybody remember which way they did it? How many people actually drew a ray diagram? Patterns? Math? Most people did math. Okay, interesting, because in the other class, most people drew the ray diagram. Okay. I wouldn't suggest that one way is necessarily better than the other. It's just 2 different legitimate ways of answering it. All right, now question number 1. This is the challenge question. It's a tough question. The good news is this is definitely one of the hardest lens or mirror equations that I've seen on an exam. You're going to have a quiz tomorrow on this stuff. The quiz question tomorrow will not be as challenging as question number 1. Okay, pay attention to it, because it's a good question. But what you see is not usually, at least, as hard as what we see up here. This one says, at what distance above this page would a convex magnifying lens... Listen, I don't like that word convex. It's like a swear word. Let's translate it. Convex, concave, don't want those. We want converging, diverging. If this is a convex lens, then it's a what? Converging or diverging? Christian, what is it? Converging, good. So let's translate it. Let's get rid of that word convex. Let's translate it to a converging lens. That means the focal length is positive 10. Now, if in this case you forgot to do the translation, you probably would have gotten away with it because you would have made f positive 10 by forgetting to make it negative. But sometimes it's not converging, sometimes it's diverging. That's when you really have to focus on that. All right, so let's write down that the focal length is positive 10.0 centimeters. We want the image to be upright and 3 times as tall. The magnification, therefore, will be positive 3. Make sense? 3, because 3 times as big, and it's upright, so it's got to be a positive magnification. If it was inverted, we'd make it a negative magnification. At what distance above the page would the lens have to be held in order to see the image of the letters appear upright and inverted, or upright and 3 times as big? That means that we're looking for the distance from the lens to the page here, the lens to the object. We're looking for the object distance. We're looking for DO. I've always told you, like, start with an equation, see what happens. If it doesn't work for you, that's okay, try another one. So let's do that. Let's say 1 over f is equal to 1 over DO plus 1 over DI. 1 over f is 1 over 10 equals, we don't know what DO is, that's okay. We don't know what DI is, that's okay. We got 2 unknowns there, but we just try another equation, right? Let's try now my other one, magnification is equal to negative DI over DO. You could try HI over HO, but you're going to see in a minute why DI over DO is what we want to use here. M is 3. Negative DI, we don't know that, and DO, oh, we don't know that. We have a problem now, and that is that we can't solve for a variable, any variable, with using either equation. What do you learn in math class? When you have 2 unknowns, you just happen to have 2 equations with the same 2 unknowns. Let's do a little substitution, yeah. Let's rearrange this to solve for DI. DI is equal to, take the DO up by multiplying, I get negative 3 DO. Does that make sense? I don't know what the value is, but I know that DI is 3 times the object distance. Now, let's replace DI right here with negative 3 DO. Now, this doesn't look pretty, but at least I have one equation with one unknown in it. It's awkward to solve for, there's no question about that, but at least we can see at this point that it is solvable because there's only one unknown in there. I want to simplify this a little bit. I want to say 1 over 10 is equal to 1 over DO, subtract 1 over 3 DO. I just want a positive DO on the bottom. That's the same thing, isn't it? 1 over negative 3 is the same as subtracting 1 over 3. Now, usually we can use that little calculator trick. Here we've got to do a little fraction addition here. We're going to say 1 over 10, find a common denominator here. What's the common denominator between DO and 3DO? No, the common denominator is not DO. The common denominator would be 3DO. We can say 1 over DO is the same as 3 over 3DO, right? You multiply the top and the bottom by 3, minus 1 over 3DO. Does that make sense? You can subtract those, right? 1 over 10 is equal to, what's 3 over 3DO minus 1 over 3DO? 2 over 3DO. Now you can see how it's possible to solve this, right? Take the 3DO up by multiplying. Take the 10 up by multiplying to the other side. I get 3DO is equal to 20. DO ends up being equal to 6.67 centimeters. Tough, tough question. I think, at least, a tough question. Did anybody happen to manage to get that? If you didn't, I wouldn't panic about that at all. Like, that's the question that's going to separate, like, you know, somebody that gets a 98 or 100 from somebody that gets not a 72 or a 74, but that's going to separate 98, 100 versus, like, you know, 92, 94 type thing. You don't get that question, you still get a really, really, really good mark on a test or an exam. And if you happen to get the right, get the right questions, still could even get 100 conceivably. This is definitely a harder than average question. Okay.